Neural networks pose a challenge when it comes to training. Training a neural network requires utilizing a set of training data to modify the model's weights in order to produce an accurate correlation between inputs and outputs. This is achieved through the use of an optimization algorithm, which explores a range of possible values for the model's weights and aims to find those that lead to optimal performance on the training data. Optimizing learning is a process of improving our knowledge and skills through strategic and efficient methods. It involves setting specific goals and implementing techniques that best suit our individual learning styles. By continuously striving to optimize our learning, we not only enhance our abilities, but also maximize the potential for long-term retention and growth. Through this process, we are able to continue expanding our knowledge base and adapt to new challenges and opportunities. In short, learning as optimization is a continuous journey of self-discovery and growth. Neural networks using deep learning algorithms are able to learn how to link inputs to desired outputs by using a training set of sample examples. The key to this learning process lies in identifying a set of weights in the network that can effectively solve the problem at hand. This process involves incremental updates to the weights, resulting in changes to the model's performance at each step. By doing so, the iterative training process aims to tackle the optimization problem of finding ideal values for the model's parameters, i.e. weights, that minimize error when evaluating the training data. However, this optimization problem is complex and difficult to solve, requiring a targeted approach. The challenge then arises: what precisely makes this a challenging task to achieve? Important aspects of the error landscape, prominent characteristics of the error terrain. Training a neural network involves solving a specific type of non-convex optimization problem that is particularly difficult. This challenge can be attributed to the characteristics of the error surface or landscape that the optimization algorithm must navigate in order to produce an accurate solution. The optimization of neural network weights is complicated due to various factors, but three key features of the error landscape are often cited as major obstacles: the presence of local minima, flat areas, and the high-dimensional nature of the search space. This complexity is evident in backpropagation, which can be slow when dealing with multi-layered networks that have a non-quadratic, non-convex, and high-dimensional cost surface containing numerous local minima and flat regions. The points in a function's domain that have the lowest values are referred to as local minima. Local minima are those points within a function's domain that have the lowest values. Local minimal or optima are areas of the error landscape where the loss is relatively low. These regions can be likened to valleys, where solutions appear to be favorable compared to the surrounding slopes and peaks. However, in the broader context of the entire landscape, these valleys still have a relatively high elevation, and there may be even better solutions elsewhere. One challenge is determining whether an optimization algorithm has landed in a valley or not. To mitigate this, it is recommended to begin the optimization process with a high level of noise, allowing for a wider sampling of the landscape before selecting a specific valley to descend into. In contrast, the lowest point in the landscape is known as the global minimum. Neural networks may have one or more global minima, and the difficulty lies in the fact that the difference between local and global minima may not have a significant impact. Therefore, the focus is often on finding a good enough set of weights, rather than seeking the global optimal or best set. This approach is typically more feasible and desirable. Regions that are flat, also known as saddle points. A flat region or saddle point refers to a location on the landscape where the gradient is zero. These areas are typically found at the lowest points of valleys or between peaks. The issue arises when the lack of a gradient makes it difficult for optimization algorithms to determine which direction to move in order to enhance the model. However, there is growing evidence that suggests local minima and flat regions may not be as much of a hurdle as previously thought.